So this is problem number 4. It's from the 2011 BC exam. It was on Form B that year. And it's a non-calculator question, and the setup is similar to a lot of other free response questions you've probably seen. We've got a differentiable function f of x. The domain of this function is 0 to 10. They give us the graph of the function. They give us some information about area. They say the area between the graph of f and the x-axis from 0 to 5 is 10 square units. And then the area of the region enclosed between f and the x-axis from 5 to 10 is 27 square units. Then they give us some information about arc length at the end of this here. Arc length of the portion of the graph of f between 0 and 5 is 11. Arc length for the portion of the graph of f between 5 and 10 is 18. And then they tell us that f has 2 critical points, and they have x values of 3 and 8. Now if you check out part A here, part A says to find the average value of f on the interval 0 to 5. So if you know the formula for the average value of a function, it's 1 over a minus b times the definite integral from a to b of the function you're looking for the average of. This isn't that difficult to carry out. You're going to have 1/5 times the integral of f of x from 0 to 5. And if you think back to what we were told that the area between f and the x-axis between 0 and 5 is 10 square units. Now the only adjustment we'd have to make would be because that region sits below the x-axis and a definite integral computes assigned area, we would just have to realize that we've manually got to make that amount of square units negative and then multiply by the 1/5, and we end up with -2 for our result for part A. Part B should be pretty straightforward as well. We've got this definite integral that we're asked to compute. If you use the fact that a definite integral is a linear operator and break it up across addition, you can have the original definite integral broken up into the sum of these two simpler definite integrals. Because a definite integral is a linear operator, we can also factor constants out in front of definite integrals, and that's exactly what I've done with the 3 as I've gone from this line to this line. And so this integral right here is definitely something that we can carry out. The antiderivative, using FTC, fundamental theorem of calculus, we can go ahead and take the antiderivative of 2 with respect to x, which is 2x. We would just have to evaluate that at 10, evaluate that at 0, and take a difference. And then this integral right here, once we've got that 3 factored out in front of it, we can use the area arguments that were provided with the details of to help finish off this first half of the problem. And so if I just copy down the 3, and then I realized that I was dealing with 10 square units down here, and then 20 square units up here, but just like we did in part A, this is below the x-axis, but that's above. So the integral from 0 to 10 of f of x would be -10 plus 27, so 17. Just multiply that together with the 3, evaluate this antiderivative at 10 and at 0 and take a difference, and you get a result of 71. In part C, they ask us to take this new function, g of x. Now, g of x is definitely dependent on f. It's defined as a definite integral, so the independent variable in the function g is actually that upper limit of integration. And then we're asked to figure out what intervals the graph of g is both concave up and decreasing on. Well, if a graph's concave up, you should realize the second derivative of that graph is positive anywhere where that's happening. And if a function's decreasing, the first derivative of that function has to be negative anywhere where that's happening. So we basically need to figure out where g double prime is positive and g prime is negative simultaneously. And if we're trying to analyze that, we might benefit by constructing a little sign chart here for g prime and a sign chart for g double prime. Before you're going to have those sign charts come together, you do need g prime and you do need g double prime. So g prime, this is something you've probably done quite a bit of if you've been looking at these free response questions. We have a definite integral right here. The variable in the definite integral is in the upper limit of integration, and what one of the parts of the fundamental theorem of calculus says is that you can take the derivative of a function like this by copying down the function that's within the integral, so copying down the f in this case, but replacing the dummy variable with that upper limit of integration. So basically that says that the derivative and the definite integral are inverse operations, and we're going to end up with g prime of x being equal to f of x. And then if g prime of x is equal to f of x via fundamental theorem of calculus application, the second derivative of g is going to be equivalent to the first derivative of f. So if we think about this sign chart for g prime, We would need to know when G prime is equal to 0. When does G prime have the potential to change signs? Well, G prime is equal to F, and F changes signs as we pass through the X value of 5, right? F changes from negative to positive, therefore G prime changes from negative to positive since it's equivalent to F, and we've got our sign chart for G prime completed. Now G double prime, you do have to make sure you're looking at the right thing. So G double prime is equivalent to F prime. Well, the way that we're going to determine values of F prime from this graph is we're going to look at slopes, right? If you're looking at a graph and you're trying to determine values of that graph's derivative, as we are in this case right here, we're going to have to look at the slope of the graph. So the slope is negative, 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 0, positive, 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 0, and then negative for the remaining stretch of the graph until we end at 10. And so we do need to know when the first derivative was 0 at this horizontal tangent and at this horizontal tangent, and that's where this last little bit within the problem setup is useful. F has 2 critical points. Remember, critical points are locations where the derivative is either 0 or undefined. In this case, based on the graph of F, it seems pretty safe to say that the derivative is 0 on F at the x of 3, and the derivative is 0 on the graph of F at the x of 8. So we don't have vertical tangents or cusps at these critical numbers 3 and 8. We definitely see horizontal tangents at them. We just kind of went through the progression of the sign of the derivative: negative slope, positive slope, negative slope. So there's the progression of signs for G double prime, which is equivalent to F prime. So what can we conclude with here? So the graph of G is concave up when G double prime is greater than 0. Graph of G is decreasing when G prime is less than 0. These things happen at the same time between 3 and 5, right? We're looking for when the first derivative is negative, which happens from 0 to 5, and when the second derivative is positive, which happens from 3 to 8. So where do both things happen simultaneously? 3 to 5, and that's where our graph of G is going to be both concave up and decreasing. Last part of this one's probably the trickiest of the pieces here. They give us this new function h, and this new function h is dependent on f. They were nice enough to provide us with the derivative of h here, so h prime is equivalent to f prime of x over 2. And you can kind of confirm that this is the derivative of h by applying a chain rule to this right here. But what they ask us to do with h is they ask us to find the arc length of h on the interval from 0 to 20. So what kind of sticks out to me as being sort of weird is that this interval is supposed to range from 0 to 20, and the graph of f is only a graph that's got a domain of 0 to 10. So this seems a little bit weird. We're going to have to probably make some sort of adjustment later on is what that kind of implies to me. And what I'm going to do is I'm going to try to just kind of recall what the curve length formula says, the arc length formula says. The length of a curve on the interval 0 to 20 is going to be the definite integral from 0 to 20 of the square root of 1 plus the derivative of that curve squared. Well, we know what the derivative of this curve is. The derivative of h of x is f prime of x over 2. So if I replace h prime of x with what they tell us h prime is equal to, I end up looking at this. Now, it seems like, yeah, we're going to have to do some adjusting with these limits of integration. And also, we haven't really used this bit of information that I have highlighted up here right now about the arc length of f. And it seems like we might have a little bit of a use for that right now because of the fact that f prime is now part of this curve length formula. Only issue is it's not f prime of x, it's f prime of x over 2. So if we think about the fact that we are sitting within a definite integral right here, and there is technically an inner function inside of f prime right here, we can try to do a u substitution. And if we try to let u equal that inner function, x over 2, du dx ends up being 1/2. And so what we can replace the dx with is going to be 2 du. But if we're replacing the variable of integration with a u, and it was originally an x, we're going to have to figure out what u value corresponds to this x value right here. So we've got this statement where we've said u is equal to x over 2. Well, if this is an x and we're trying to turn it into a u, it makes sense to say, okay, well, we're going to put that x into our relationship between x and u, the equation that relates those two, and then 20 divided by 2 gives us a new upper limit of integration of 10 as a u value, and then the lower limit of integration doesn't change, but we do the same calculation with it, right? 0 divided by 2 to turn that x value down here into its corresponding u value, and we get 0. And so if you transition the limits of integration from 0 to 20, from 0 to 20 to 0 to 10 by doing the appropriate substitution steps, and recognize that now this is a curve length formula for f. You know the curve length from 0 to 10 of f is going to be 11 from 0 to 5 plus 18 more the rest of the way from 5 to 10. So the total curve length is going to be 11 plus 18, or 29. We just can't forget about this 2 that snuck in because of the substitution that we attempted to do there. So kind of sneaky, but that's how you would handle Part D.